Hello and welcome. My name is Luciano Lucas and I'm here today to do the introduction to Aivia 9. We're launching it today. And before we get to that, just wanted to say a couple of things about the last few months. It has been a pretty crazy year for everybody. And first of all, thank you very much for joining. Appreciate it. I know everybody's busy and it's pretty crazy few months for everybody. So over the beginning of the year with COVID, everybody had to start work from home. Same from us. We're just in the office today to do this webinar in our normal studio, but still everybody else in the company is working from home. Thankfully, no one got ill within DRVision. It's been, of course, it has affected many people around the world, and many have died. So we have been following that and send our condolences to all of those affected. We have tried to help as much as we could by creating resources like Aivia Web, and we offered that for free for 2 months. For everybody to continue to work from home if they are, healthy and working from home, and we also introduced a number of other solutions. But it has been really a turmoil in terms of health. More recently, and as you all know, there has been civil unrest here in the US and protests over the whole world. I wanted to read a brief statement for you from us, which we'll put out in full after, in the next couple of days. We'll put it out in full. But I wanted to say that the brutal killing of George Floyd and countless other African Americans at the hands of the police is shocking. It has shocked all of us here at DRVision and is utterly unacceptable. Horrors like these should not occur in our society. We stand in solidarity with the peaceful protesters and the memorials that are happening across the globe. And we also, together with the people protesting, we demand for equity, equality, and justice. We send out deepest condolences to George's family, as well as Rayshard's family. As you probably know from the last week or so, there's been more troubles, as well as their friends and communities. We hope that these tragic deaths, along with those of others even before, and there's a long list here, mark a moment in the history of America and the world that will finally push everybody to take decisive action against police brutality and racism. Internally, we have been discussing both at the company level and as individuals what we can do to help get rid of racism, essentially. And at a personal level, there's people already have taken action themselves, and as a company, we'll also be looking at ways to do that. But for now, most of us are listening, learning, or unlearning, as it may be, and listening carefully and trying to take actions that are actually helpful. So for now, it's a moment of introspection, a moment of planning, learning, and actions will come of this. So that's all I wanted to mention before we go. So you may notice that the tone of the presentation may not be as bubbly or happy as other product launches that I've done, but this is I think what I can do. I am, of course, very excited for what we've done, and we think it's important to continue with the work we're doing and release it. We actually had it planned, the release, for last week, as you all know. We didn't do it because it coincided with key memorials for George Floyd, as well as an online action to shut down Academy for one day. on the 10th of June. So with all of those and to show respect to the cause, we decided to shift it by 1 week to today. So we think it's important because we are developing tools here that help the community that is trying to find both therapies and vaccines for COVID and other diseases. So we wouldn't do anything good by stopping what we're doing. I think we need to push ahead together with the community, the scientific community. And so today I'm excited and I'm honored to be presenting you the latest functionality that we've developed for Aivia and for the image analysis community, life science community. And that's what we'll be talking about the next few minutes. We have a presentation and then pretty nice demo. I am actually really excited about what we've done. This is probably one of the best, if not the best, release we've had in the last 3 years since we launched the first Aivia back in April 2017. So without further ado, I'd like to progress the actual presentation. Just a moment. So Aivia has we over the years have added different products to the Aivia product family. It now includes Aivia itself, Aivia Cloud, which is a tool for training and applying deep learning models for segmentation, restoration, and virtual staining. Aivia Web, that you can deploy, use Aivia on a web browser, and Aivia Community, which we launched earlier this year, and it's a freeware that allows you to view data and create video animations, as well as create annotations and preview results. This is what we've done over the last few years. Really a lot of development. I'm not going to go into all the details. And in addition to this, we also added Aivia Community, which is derived from Aivia itself, and Aivia Web, which we'd actually offered for free to the community while everybody was adjusting to the COVID situation and being pushed out of the labs to practice social distancing. It turns out Aivia Web is really a very practical, useful tool. So we're actually rolling that out as a fully fledged product now the next few days. And you'll hear more about that later on. So this is the current infrastructure that we have. There's Aivia Cloud for training models, and that's connected to the Aivia Local. This is what most people have, is Aivia Local that can then send jobs to the cloud. You can also train locally. This tool does all the visualization, training and applying, set up and monitor jobs, and do all the things that you normally see Aivia do. Aivia Web is a deployment of Aivia in the web. That's what we use for all our online workshops nowadays. So you have your own version of Aivia running on your own browser as you watch one of our instructors do the presentation. And Aivia Community, which I encourage you to try if you have not tried it yet. It's free download. So today, introducing quite a lot of new functionality. As I said, probably the biggest number of features and the highest impact features we've added, perhaps on par with Aivia 8 when we first introduced all the cloud platform. Firstly, I want to mention we also added a few plugins. So we have 2 new plugins for CellPose and StarDist, which are good tools for image segmentation using deep learning. We also have a brand new tool or part of Aivia, which is a search bar or action bar, depending on how you use it. The multi-scale image analysis, where we'll spend most of the time today. Instant save, also very exciting, as you will be able to quickly save your data without resaving all the voxel data. Lots of new rendering options, including one that renders just what you need within an ROI or multiple ROIs. There's quite a few other features which I encourage you to explore. You'll be able to download Aivia today and try it out, including additional support for some file formats that we already supported in some way, but we expanded the format, expanded the support. So these pictures are from ASCB last year, in the time before COVID, when conferences actually happened in person and you could, shake hands and go for drinks and so on with your friends and your colleagues. So at the ASCB EMBO 2019, we asked biologists that came by the booth and that we met to draw out a cell. That was part of one of our marketing campaigns, and you basically got a t-shirt. Don't have one here, but you got a t-shirt for making one of these drawings. And I wanted to share all of them with you. I think this is pretty much all of the ones we got. And these are hand drawing sketches made by biologists. And you can look at this and try to identify a few common threads. And that's what I wanted to do here. So not only they're beautiful drawings, but there's interesting kind of pieces of information here that we take inspiration from. And we take inspiration for Aivia not only from talking with customers and talking with users and talking with collaborators and partners, but also from random interactions like this. And if you look at all these pictures, you can just pull a few out. You can see that there's a few common threads here. They are free-form, so not squares. They're free-form shapes. There are multiple compartments. Quite often, almost always, there are multiple compartments. There is hierarchy. One is inside the other, and one is related to the other. And there are different scales. So you will have images that are small, and you just have one cell, and you look at it with a super resolution microscope, and that's all you need. That's your universe. But you may also want to look at the whole embryo of a mouse, and then you don't care about single cell. You care about how do the organism look like. So with all these thoughts in mind, we started to think about how can we facilitate this kind of thinking in this kind of image processing, image analysis. So we started to think about that, and being, as you know, we are based in Seattle. We started to think about that and kind of distilled it down to the concept that we are introducing today. So this organism to organelle concept. And it is a multi-scale image analysis kind of paradigm. And we're very excited about this. It does really change how Aivia behaves, because typically Aivia and other tools behave in a single scale. And you have a way to analyze your data or a pipeline that works for this one scale, for this one type of image. But if you want to do it across a range of scales and many types of images, it can be very challenging sometimes. So we tried to break those and use these key components or key thoughts that came out of these drawings and our understanding of what biologists want to do. And I'm a biologist myself. Try to kind of distill that into a new concept, an innovative concept that we want to introduce into Aivia. Now, before we jumped in, we actually went to study this and tried to figure out, is this actual? And it turns out it is really the case, as every biologist here will be well aware. Things are really like this Russian doll with things inside things, inside things, inside things. And you can go down to a small scale and you look at cellular machinery, in this case a nuclear pore, how it's organized, and you can use super resolution microscopy to look at those, or even EM. Then if you go up a bit, you look at organelles, full organelles like a whole nucleus, or ER, mitochondria, and all of these components, vesicles in the cytoplasm. If you go a little bit further up, it's full cells with all the organelles inside, and then further up, tissues, systems, or organoids, and this is an organoid on the top. And then beyond that, when you put all the systems together, you get full organisms, which can be very simple organisms like a yeast, or very complex like a mouse. So this is really the case. So we went back to our images and we tried to kind of analyze that in that way. But it was very difficult because like most image processing tools out there, Aivia was set up to analyze one compartment at the time, and it had really no relationship between them. So now we have done quite a lot of work in order to analyze all of the compartments and keep those connections together. Today I will cover the full range that you see here. I'll talk a little bit about each one of these examples in the next few slides, and then spend a little bit of time in Aivia itself demonstrating how it looks. Yeah, that's what's happening next. So image analysis, the standard way that you'll see in most software is that it works on a per image basis. You get a total number, can detect the total number of objects. You know where each object is. It will tell you the X, Y, Z coordinates and time for the whole image. You can segment one object type at a time. So you can detect all the nuclei, and then you have a spreadsheet with all the nuclei. Then you have all the cells, and you have a spreadsheet with all the cells. And they're kind of separate. That's the next thing. So they're unrelated to each other. You don't know which nucleus is part of what cell, typically. With the approach that we are introducing here, we're really looking at identifying the biological elements and the meaning that this biological element has in the context of the whole sample. And the whole sample may be just a cell. It may even be just a nuclear pore if you have that kind of resolution. But it would be a full cell, probably at least, and then all the way to a full organism with multiple regions inside. So with Aivia 9, you can detect the number of objects per biological compartment. And we have quite a lot of compartments available for you to use. You get absolute and relative position. So absolute meaning versus the image, where is the object, and versus the compartment that it belongs to, where is the object or where is the element. You can compute distances between organelles and the different compartments, which is really handy. And you can segment and create complete models of these multi-scale models of your sample, which is very exciting and looks really cool. Because we know what the hierarchy is, we keep it, and we can tell exactly which nuclei belongs to which cell and what mitochondria might be close to that nucleus. So that's high level what kind of measurements we have. I have another list that looks at it in a little bit more detail. So what does the recipe actually look like? So when you enter Aivia and you want to do it yourself, what does that look like? Well, it initially looks like this if you have everything turned on. So I turned on cell detection, nucleus detection, and then 5 types of vesicles. We could have even more, but we kind of capped it at 5. You don't have to have all of this. You could have just cell plus nucleus or cell plus 1 vesicle. In this case, I turned everything on, but you can have pretty much any combination of these. And depending on what you turn on, then you see it here on the recipe or not. It will disappear. So you can have a pretty small recipe or a longer recipe. Now, if I was to expand one of these elements, so for example, the whole cell detection element, I'm going to get that to that next. It looks like this. It has a smoothing filter pre-processing step. It has, so that's the pre-processing step. Inside of that pre-processing step, you can choose which smoothing you want to use. So, morphological, average, Gaussian, or median. There's also the choice to do background subtraction or not. So if you have a pretty difficult image to segment and you have a lot of background, you may want to use this. And then it gives you the option to remove the background before you do the processing. And the final one is partition. So you may want to, if the cells are touching each other and you want to separate them, this is the step you would use. You turn this on, and if you turn it on, as it is on right now, it gives you these parameters, the range of the object that you're looking for, what is the size or the distance between the center and the edge of the object, and then if you want to smooth the output or not. So you have 2 smoothing. This is the smoothing filter for the input data, so you're smoothing the input data, and this smoothing at the very end is smoothing of the mesh that you're outputting as a result. And finally, if you're doing nuclei, so if you had this nuclei detection open instead of the whole cell, you would have one additional option, which is some correction for the position of the nucleus. Sometimes, due to problems with labeling primarily, you may have uneven labeling on a cell. For example, a cell, I'm talking about cell because it's easy to explain, but if you have a cell with the cell, the cytoplasm is labeled and the nucleus is labeled, you may have poor labeling of the cytoplasm where the nucleus is. And it may look like the nucleus is actually outside of the cell, outside the cytoplasm. That's not really possible, and we know that. So you have the option to extend the cell to include the nucleus, or crop out the bit of the nucleus that is kind of poking out of the cell. So that's the two options, or do nothing and leave the two kind of intact. Additionally, and this is also a very exciting development, we've added this button right at the top. For now, it's only in this recipe. We do plan to roll it out on other recipes in the future, and we do have a very exciting prospect for increasing the intelligence of this button. But for now, this button sets the thresholds, sets the threshold parameters. This one here sets this minimum cell intensity, that number there, sets it on its own. The aim is it should always be good enough to give you a preview. When you're doing a first segmentation, you create a crop around, or ROI around the object of interest, you hit that button and it should always show you a reasonable preview. And this parameter here is sensitive, so it responds to adjustments that you make to the smoothing. So if you change it from 9 to 2 or 1 or 10, you should hit that button again because it will adjust the parameter. Equally, if you're doing the remove pipeline background, so remove background, there will be another piece of information that it asks you, which is the typical cell diameter. And depending on what you put in there, it will also be worth hitting that button again so that the threshold gets adjusted and you get a good preview. So this is something that we find is really, really powerful, really useful. And we're looking to add this kind of functionality to other recipes, as well as improve this functionality even further so that it optimizes more of the parameters, not just this one. If we need it, and my demo goes really badly, I will show you this video later, which is one of my demos. But for now, I'll just go forward, and it might come back if the demo doesn't run well. So what types of measurements specifically are we adding? And I should say, if you've never seen an Aivia presentation, or if you've never seen Aivia, this is not the full list of parameters that we can measure. We can measure many, many parameters that I'm not listing. I'm just mentioning the types of new parameters that we're adding. And even for each one of these types, there are multiple parameters inside. So to do with morphology, we now can have information like the ratio of the volume between the cell and the nucleus, the cell and the cytoplasm, cell and the organelles. We also know the contained physical volume for each for the vesicles or for the organelles that are inside the cell. And we know, of course, information to do with sphericity, diameter, surface area, and many, many other parameters to do with every single element of that cell. So that's the morphology. Then in terms of intensity, we know the intensities for every object in every channel on every time point. So there's full mapping of that. In terms of position, we also know, because we know where we have the absolute and the relative positions of every single object and the hierarchy, we then can calculate distances between everything and everything, almost. It's everything that is logically connected. So we don't try to calculate everything to everything because it is computationally expensive and unnecessary in many cases. So we're working towards building a model that looks something like this. Of course, this is a 2D cross-section of a 3D cell made by Cathy. But we're working towards doing that, and let's see how far we've gotten. So with the count, we can, of course, count the number of objects, a number of biological elements in every single one of those compartments. And I keep talking about a single cell, but really it could be a whole embryo, and you will see that too. And in that case, it would be the number of objects within an organ, for example. And later I'll show, a brain and the liver and the number of cells inside of those two organs. So when it comes to visualizing the results and exploring the results, this is the kind of experience you will have. I'm looking here at a 3D data set with 4 channels. Once you run the recipe, you have all of the objects visible here, and you can interact with each one of them. I'm already showcasing, actually in this video, showcasing that we also have transparency, which is unique for each object set. Excuse me, it's unique for each object set. And I'm also showing, and we'll show in a moment, that you can change the colors of the display of the meshes based on any parameter that you like, that we've calculated. So for now, they're colored based off of the input channel. That's the standard. So when you finish the recipe, the objects are colored, color matching the color of the input channel. But later on you can change that, and that's what I'm doing here. So Visical 1, changing that. Right now it's volume, but you can change it to other things. And if for some reason volume is not the one you want and nothing else is shown, then you can turn other things on in the spreadsheet tab, and I'll do that later in the demo. Once you've created the analysis and you've color-coded everything the way you want it to be, you can then create really impressive video animations of your full model, cellular model. Here, in this case, we're using nucleus so this is nucleus and vesicles. So we have spots to display these vesicles, but we also have the cell membrane, which is a mesh, and we have another type of organelle, which is this red kind of mesh-like organelle around the cell. So you have the option to use both points or spots or spheres, as well as fully free-form meshes. So this data set was actually, there's a misspell here, it's Leica. Leica, not what's written on there. So it's Dr. Ed Leica from 3i. He created this beautiful data set which represents gastric gland organoid. The data set is actually, the sample is from a lab in China. Shuao Biao is the researcher, and this is done on the Mariana's light sheet microscope from 3i. So beautiful data set, really cool sample, and great imaging from Ed Leica from 3i. So typical imaging would show, typical analysis would show this kind of analysis. If you have a good piece of software, it would do this. It would detect everything correctly and display it correctly in 3D, multiple organelles, and then you could count. You could say, okay, there's 16 cells, there's 1,581 vesicles, and therefore there's an average of 98.8 vesicles per cell. And that's it. So you put that in your publication. Now, this might be okay. It might be sufficient in some cases if you don't expect any variability between the cells. But in nearly every case, there is significant variability. So let's have a look at, if we have Aivia 9, if we are using the multi-scale image processing that I described, and you have all this hierarchy, then you can have information on a per cell basis. So this here shows cell number 7. It has 157 vesicles. That one, just that one. This one has 146 vesicles. This other one, number 13, has only 52 vesicles. And this one has 20 vesicles. Now, in this case, it's relatively simple. It's a relatively small data set, and there is no additional complexity. But imagine that you had a third element here, maybe another region of interest over here, and you want to know, are the cells with lots of vesicles the ones close to this reference point? that's also something you could do with Aivia and know that. And even if you're not doing such complex image analysis and you just want to know this, it's perhaps very important to know that there is a very large distribution of number of vesicles per cell, and that 98 is really not that representative when you look at the spread. So that's something that is now possible in Aivia 9, is to know per cell what each one has. So let's start to look at the second data set. This is a data set from Philip Keller at Janelia Farms, and was imaged on the SimView light sheet microscope. This is now a few years old data set, but really nice, and it's still used today for the cell tracking challenge. If you're into doing that, it's a really cool challenge. So in this case, we detected all the cells, and we have actually detected multiple regions within this Drosophila embryo. And there's this midline, and there is a tip on the top part of this, which you'll see in the next slide. And then we can relate all of these. And also, there is the whole embryo. So this is the whole embryo, is one element. Then we have another element, is the midline. Another element are all the vesicles, or all the cells inside. So in Aivia, you will find the standard nomenclature is about a single cell. So it talks about cell, cytoplasm, nuclear envelope, nucleus, and cell membrane. It talks about these 5 elements, but you can rename them anything you like. Especially for what we call vesicles, you could call them anything, and they can be free shape and spots. So let's look at this analysis in detail. So with Aivia did the rendering here, first renderings, volume rendering. Then the second one is detection, and it's just color-coded by volume. So this was already possible with Aivia before. So you could detect everything, color-code by volume. That's standard. And other tools can do that kind of thing too. Now, this is a distribution of volume. So you can see here, there's a certain distribution of volume. And then we also detected these 2 regions. So there's now 2 regions plus the whole embryo, right? So 2 regions, and we want to know how many cells are in each region and how do they, what is their distribution? So this is the volume distribution for the cells that belong to this midline. So this distribution and this distribution. So the XY axes are the same. I kept them the same. The only difference is now that there's a lot less cells, and that's the distribution. And for the tip, that's what it looks like. So that's the distribution for this tip area on the very top. And I've color-coded here the cells based on their distance to the center, I believe, to the center of that region. So that top region there is yellow if it's close to the center and blue if it's far away from the center, so it's on the edge. So that is something that is new and wasn't really possible before. And another thing that is not possible, so here we have the whole embryo, this example here, we have the whole embryo plus this mid-region, and the cells in the whole embryo are color-coded to the distance from the edge of that region. And that's the distribution of the distance to the edge of this region. So some parameters that are now possible, of course, detecting all of them is easy, but then knowing things on a per region basis. And the region can be arbitrary, or if it's labeled, then you can detect it automatically. So here we know we have 1,161 cells right at the top. In the small region, we have 177 cells, and we have a full description of the average volume. Actually, have average volume plus standard deviation. I didn't put that on here, but that's also available in Aivia. You have average and standard deviation. Of course, you can also get the distribution for each region. So you get volume, intensity, sphericity, how many cells intercept with the edge of the region. That's also very interesting. So for this tip region, how many cells are actually intercepting with that outer shell? That's important, for example, if you're doing exocytosis studies and you want to know how many vesicles are actually getting to the membrane. Out of all the ones that are in the cell, how many are getting to the membrane? So that's one example. or how many cells are making a particular layer of this embryo. So the ones that are on the edge are part of that layer. And then for the center region, a lot of new additional information, as well as the distance to the center of that cell region, which is 150 microns if you're interested. So the average distance is 150 microns. So these are things that are now possible. Aivia also does scatter plots, so you can use those. That's what it looks like when you do a scatter plot. And in this case, I have distance to nearest edge of this region and the volume, and that's and then it's color coded by sphericity. So all of these types of measurements on the far right are new measurements that are now possible, and they are possible because we know what each component, how each component relates to another component, and we can measure that. The final data set that I will highlight is this embryo, mouse embryo from Gabriel Martins from the IGC back in Portugal. This is a beautiful data set imaged on optical projection tomography microscope built by Gabby. And it shows a mouse embryo. Here we detected multiple regions and then multiple cells within those regions. And this chart shows mean intensity and then distance to nearest edge of the cell. So some cells, some objects, or some cells in this case, are inside, some are outside. And they are color coded by whether they are inside or outside. So relation to frame means they are either inside of the region or outside of the region of interest, meaning in this case I think I'm looking at the brain as an example. So what does that data set actually look like? So here I have the liver. The liver has lots of cells inside. I color coded those cells on the distance to the center. Also detected parts of the brain and the eyes, and then color coded all of those cells to their distance to the edge of those 3D regions. And we can get full analysis on those. So that's what it looks like in some more detail. So the two regions I'm looking for are this one here between the eyes, so it's a part of the brain, and the liver down here. And you can clearly see the distribution pattern here in ZY and ZX axis for these two regions. This is also interesting if you're doing drug distribution on a tumor, and you've resected a tumor, you sampled it, do maybe a whole mount, and then you image it. You want to see, is this tumor actually hypoxic, and where does it stop? I mean, where does the hypoxic part finish, and where is the viable part? And how much is my drug entering that viable part? Is it getting all the way in or not? So you could use, if you have images like that, you could use this kind of approach to see how deeply a tissue is being invaded by a drug or by other cells. If you're looking at, for example, metastases or any other invasive event. And the final data set that I want to highlight, and I might not get to show this in the demo, is this one from Wanqing at the University of Washington here in Seattle. And this shows a single neuron. It's actually really beautiful data set. It has many labels. I think there's 3 labels for different points of connection between different cell types within this sample. It has one neuron, which you can kind of see meandering around here. And then there's 2 or 3 labels that show, when they colocalize, it shows points where the cells are interacting with each other. So detected the neuron with a mesh. We could have detected it also with a neuron analysis, but for this, multi-scale, we are using the meshes. And we have multiple additional cells being detected. If you look closely at this point, early on, right here, you can see there's different types. So there's this is the main neuron cell, and then there's this like 3D meshes that represent one of the labels, and the other label is represented with spots. And where they interact is also are the points of interest. So in this case, I color coded it on the distance to the nearest neuron. So that's what that shows. Oops, sorry. Okay, so that's all the data sets I'll show on the presentation. I'm going to show you the rest of the slides and then the rest of the features, and then we're going to go and have a look at Aivia itself. So one other cool feature that has nothing or little to do with the multiscale image analysis is a generic feature for controlling the volume rendering quality. So we now have a little slider that you can control anytime, and it gives you a trade-off between performance and speed. And if you set it to 5%, the volume rendering will look like this. Not great, but very fast if you need it. So you might be on a limited hardware. You may have very little dedicated memory on your GPU, so you want to do that. If you have a better GPU, you won't need any of this, most likely. So if you set it to 25%, it's already quite a bit better than that one, and you can see the difference. Single cell. So this one at the bottom here is done on the Sora from 3i as well. It's a single cell super resolution spinning disk system, and that one you've seen before. So you get it to 50%, and you start to see quite a lot of detail, and all of these artifacts, rendering artifacts, kind of disappear. And then at 100%, pretty much all the artifacts are gone, and it is the full quality image. So that's what it looks like in Aivia. You have this little slider, and you can go to, basically 1 or 2% all the way to 120%. And I dare you to try the 120%. It does have an effect, and it's experimental, as you'll see here. It says over 100%. It's experimental. It does have an effect. It makes everything a little bit darker, but more detail. So you need to adjust the lookup table if you go beyond 100%. Otherwise, just leave it up to 100%, and it'll be great with the standard lookup table. So some additional features. We now have the instant save. This will save just the updates to your results. So if you open an image that is a terabyte and you do a simple small annotation, you hit this button, the save, it will just save the small annotation into the 1 terabyte image. It will not resave the whole image. Unfortunately, that is what was happening before. We only had the option to save everything. So we would save both the image volume data and the new updates. Now it's an incremental save, so it saves just the part that is new for the results. We also have the search and action bar. I'll show that in a moment. That's really cool. And we have a lot of hopes and a lot of plans for how this is going to work in the future. In terms of rendering, there's additional functionality, quite a bit of it. So we have transparency, as I mentioned, the load on demand and level of detail. That's what LOD squared means. And we have specular lighting for the meshes. That's all new. On the measurement side, we've redone the whole measurement selection window so that it's easy for you to find everything. And also change the way you can see and find the groups of objects. So that's really nice and much more efficient to find what you need. I mentioned also we've tested and implemented plugins for CellPose and StarDist. So these are open source plugins, or open source tools that have been published. And we have created the plugin for Aivia using Python. And you can find it on GitHub. This is our GitHub right here. And the people involved primarily in maintaining our GitHub are Patrice, based in Europe, Hang Yu, here in the office, well, here in Seattle, not in the office, and Trevor Lankin, who's in Texas. And the three of them contribute to what is published on here. There's a lot of different plugins in there, but the latest two are these two, and you're very welcome to use them. You can also design your own, and we have just uploaded the API definition so that you can create your own plugins in Python for Aivia. The installation process for these plugins is really straightforward. It's just download this zip folder, unzip it, drop the file into Aivia, it becomes a recipe, and then you can use it. CellPose and StarDist are original pieces of work from two groups, or multiple people from two groups, and these are the publications you should go and check out. There's also implementations in other open source tools, I believe in multiple tools. So you can use them there, but if you're using Aivia, you can use them here as well, and build them into the rest of your pipeline. All right, demos. So this is what I'll show. Search bar, new rendering options. Then I'll spend most of the time on the multi-scale image analysis. While I'm doing that, I will show a little bit about the ROI. You get what you see what you need, and the instant save will be basically the end of it. There's quite a bit to go through. We have about 15 minutes, so I'll make sure we get it done in time. All right, let's open this up. Okay, Aivia, this is Aivia 9. You can see right there, Aivia 9, today's build. I think this is the release candidate, so that's what everybody's going to get when they install. And I'm going to go ahead and open one of these data sets. I think this one. So this is 5 terabytes. Sorry, 5 gigabytes. It's not huge. It's actually pretty small. So I've already done the analysis, but I wanted to use this data set as an illustration of how to do the analysis. That's the one you've seen before. So you've seen this data set during the videos. It's rendered here as a maximum intensity projection, but you can change it to composite mode. And the recipes are in here. By default, you might see this instead. So, you might see it like this. You can pin your analysis tool to one side, and the recipes are in here. So there it is, the 3D cell analysis with meshes, 3D cell analysis with spots. If you use the spots, then the vesicles are spots. The membrane and the nucleus, the cell and the nucleus are always meshes, but the vesicles can be spots if you want to. So I'll expand that so you can see the whole thing. You can collapse that. I will need, in this case, I will need the cell, the nucleus, and let's do two vesicles. This is fine. So I will use this channel as input to the cell. Then the nuclei are the first one. So this, like this, and like that. Okay. So that's the sequence of inputs. I'm going to set the region of interest. You can see it here. Turn it on. And this is one of the first new features I wanted to show. So this is a region of interest that you can move around, and it renders just what's inside of that region. You can move it anywhere you like in all dimensions. And you can make it bigger, smaller, and it just renders whatever is visible. So I'm going to adjust it like this. So I don't need to use any resources. I mean, my computer is good enough to do this on the whole data set, but for now, I'm just going to do it like this to illustrate this feature. So you can turn it on and off like this. And let's get started. So that part is done. I can close it. I want to apply only in this region. And I'm going to expand the first one, which is the cell. So that's actually the one I want to segment. And I'm going to use the automatic one. So you will see this will change. When I hit that, it very quickly adjusts to this number. And now if I hit preview, it will add the preview channel or the preview object set down here, which is visible in there. So it always shows me a preview. If I had let it be where it was, which I think was 13,000, and try to preview that, it probably wouldn't preview much. It would preview this. So that's what it would have done if I had not hit that automatic button. When I hit that, it will redo, as you can see, the calculations and compute the new one. And it has done that for all the channels. So let's do that now for the nuclei. So these are the nuclei. I will preview nuclei. So it gets rid of the cell and it shows the nuclei. So there they are. And maybe I want to partition this. So I do apply partition. Can make a smaller range here. and here. So I'm trying to get these guys to partition properly. Okay, that's partitioning too much now. This is over partition, so now it's correct. Okay, so that looks good. Then go to the next physical type, which is, what was it? It's the red signal, so this one. So this is creating a preview, but it's creating a preview that isn't matching very well with this. So I'm going to increase this to 6,000 so that it will match only the high intensity regions. But maybe that's too high now. So maybe 4,000. And I don't want to partition actually this. Okay, so that's pretty good match. And the final one is from this channel. So I want to try and match this. Okay, over the segmentation is too high, so I'm going to go to 8,000 and try to match just what's on there. So that's still too high, maybe 12,000. And right, you could adjust it depending on what it is that you need to do. So that's done in terms of setup. Then you can start it, and it's going to run the analysis and build the object set down here. So this is processing, as you see. Once it finishes, and it shouldn't take long, it takes maybe 10 or 20 seconds to do all of those. You then get a full rendering of this particular region. You could see that I didn't apply any smoothing to the cell, so the cell has zero smoothing here. That's why it looks kind of rough. I'm going to reapply, and you will see that the cell is now going to look a lot nicer. So this is the only time I'm going to actually show you how to set up the recipe and run it. For the other examples, I will just show the full analysis already completed so that you get a sense of what is possible in terms of color coding. Okay, so that's complete, and you can see the colors are matching. You can turn that off, the region off, and see the other cells in the context. So that's that one cell that we've analyzed, and we have the cell, have the nucleus, this physical type, and this physical type. And by default, we can color code this. So you can color code distance to edge of the nucleus, for example. You have a few other default parameters. If the parameter you're looking for isn't there, you can just add it in the spreadsheet. There's this tab here, and then you can find it here. So if you wanted, for example, count, you can type count in here, and it's going to find which object you want to add count numbers for. And then it will add that to the list. And there it is. So in this particular cell, you get the counts there. Okay, so that's for one little cell, but let's look at the full thing, one of these full analyses. For example, this one. So this one has, no, I don't need this anymore. So I can collapse that one, and okay. So here we have this group. In this case, I actually run too many things, but you can see I have the cells, I have the nuclei for the whole data set, and the vesicles. And the vesicles right now are color-coded by label, but I can do it by, I changed cell, I think class. Yeah, by class. So I want to do measurement on this one. So measurement, that's the color coding I used for the video earlier. And now they're color coded by measurement. I can select any of these if I want to know some details about them. So I can select this one, and I know this is physical 1515, just happens to be 1515, so it's selected already. And it's out of the whole cell 3, so I select whole cell 3 and physical 11 over here, and now I'm basically in this list. So this is connected up to here, and it's connected up to our charts as well, which are here. So physical 13, nearest distance to the center of the cell, and say, oh, I wanted the volume, which I don't have, so I have to calculate it here. Or the position, yeah. So the Y position. Oh, it's calculating. So I'm calculating a new measurement that I didn't have, and now I can use it here. Am I picking the right thing? So 3 physical 1 2. Yes. 3 physical 1 2. I picked the same two. Spreadsheet. Okay, so this shows distance to center of cell and distance to edge of the cell. And just wanted to show that how to set up a spreadsheet. I don't have a lot of parameters calculated for this one in advance. That's why I was kind of struggling to show you some. But here you can see them very, very nicely. Okay, so that's one of the data sets. Before I move away from this data set and on to another one, I wanted also to show you this. So if you wanted to use the pixel classifier, you don't know where it is, you can just write it in here, pixel classifier, hit enter, and now Aivia is going to highlight the region, and you can see it down here. So that's one of the uses of the new search bar. Another thing is if you want information on the pixel classifier, for example, so you can pixel classifier and it shows you our wiki. You can hit that and it will open the wiki with that page directly, so you can very quickly navigate between one and the other. I can do that again, so I can do tracking, 3D object tracking, and it goes directly to the wiki that you need in order to learn. It does also take some actions. Let me show you this example. Darken, so you can make the image darker or brighter. You can turn things off and on, or open the file. So if you want to open here, you can open the file. And if you want to see everything, there is a way. I think it's still there. Yeah, still there. So all the commands that are currently possible are here. So you can navigate to different parts of the software. You can take some actions like brighten image or open the folder, create a mesh. There's quite a variety of different things you can do. You can save. But in general, it will help you get to this is one that sometimes people forget where it is. So where is the overlay manipulator? So the thing that you use to change the scale bar. So you can select that and it will take you there. There it is. It's inside the analysis tool, inside the 3D tools, and it selects the right parameter, the right part of the software. And now you can adjust your scale bar, make it bigger, and so on. Turn it off. So that's sometimes it's difficult to find particular parts of the software. So this will help you find those parts, which is really useful. So let me open one other data set before I get to to the mouse embryo. I think it's this one. I wanted to illustrate the multi-level, a couple of things, but let's start with this. So one of the functionalities I mentioned earlier is specular lighting. That might not be apparent to everybody what it is, so I'm going to illustrate that here. And transparency. So here is the whole embryo. The transparency, of course, is just, make it transparent or not. And the specular lighting, you can see it's kind of this shininess, and you can turn it on and off here. Some people prefer it kind of matte, others prefer it more shiny. And you can combine that with other rendering modes that we have. For example, this is our point rendering mode. You can make that really cool effect in here together with the other objects. So you can combine those. There's point and wireframe, which is what I wanted to use now for the cells. So let's look closely at these cells. They are built of little triangles, right? There's lots of them. And if I have the low level of detail turned off, it always loads them at full resolution. That's what you see right now. But if I turn it on, now it loads them at lower resolution. And depending on the point of view of the camera, it will load them at higher resolution. That's really important for large data sets. So right now, it's low level of detail only. If I zoom in a bit, it starts to be higher level of detail, but it's only in a small part of the data. I'm just going to change here the color so it's easier to see. It's only on what's close to me, right? Not what's on the back. And as I move, it adjusts. Now, if you have this rendering mode, it's kind of obvious. If you have the regular rendering mode, which is solid, it might not be as obvious. So this is the solid mode. Now you can't really tell, but it's still happening. If you look closely, the objects back there are made up of very few triangles in comparison to ones at the front. Now you can tell, now you cannot, but they're still rendered with very few. The big deal about this is we're using very little amount of memory, RAM, and GPU memory to do this. That's really a big deal for large data sets or long time lapses. And it also lets us load and display much faster than it would be otherwise. Okay, so back to the full rendering. So I turn that off. And I can see these embryos. I'm going to color code them center of this region. So that's the region that I have. And it is edge, yeah, like this. Right, so these are now color coded based on the distance to that center region. And we can count, we can define what is the distance, and then look at the spreadsheet and find out how many cells are in each band just by looking at our either a chart, which we can make a histogram for distance to the nucleus. Oh, that's the wrong one. It's this one. So the ones that are really near are these. There's 261. You can go to the next band. There's 416 and so on. And if you've selected the right region in here, then it also selects from the list, and you can filter those into another subset and then look just at those separately. So all of that is possible. And some of this was already possible before, but now because there is a hierarchy and there is a connection between the different object sets that we have, you can get to much deeper insight into every data set that you look at. Okay, final data set that I'll open just to show you, because it's such a beautiful data set, is this data set from Gabby. here it is. So sorry, I have a clipping plane here probably turned on somewhere. Oh yeah, I see. Okay, so here's the raw data set. It's pretty impressive, and if you apply here an ortho slicer or clipping plane, is impressive to look through it. Lot of detail, very cool. So we then did do the analysis on this data set, and we have the whole mouse here. It's a little bit transparent now, so you can make it less. There it is. So there's the whole mouse. I'm going to make it transparent again. So the whole mouse, we have the liver detected down here, and the liver cells, and then we also have the brain, and the different brain regions can be color coded for anything, for example volume, and the cells inside of that can be color coded for distance to the center of those regions. Okay, so we're getting to the end of the demonstration. I hope you've enjoyed that. I'm just going to make here one final chart. Oops. Brain spot. Here's cell. Brain spot. Yeah, so you can interact with those like this, or directly with the scene like that, and the spreadsheet is connected up. And so we have the groups also that I mentioned. So we can go to the brain, and the brain has all these regions. In this case, we're looking at this one, which is right there. I'm going to pick the ones that are very near. Go here, and there it is, one that is actually touching, because it's just 0.6 microns. The center of it is 0.6 microns from the edge. Okay, let me go back to the presentation and see if I forgot anything important. Action bar, rendering, multi-scale, automatic pre-post processing, fast preview, complete morphological, that's all done. This is done, real-time update, and the fast saving. So that's the last thing I needed to show is this. So if I've just run the analysis on this, I can just go in here and do save. And I'm going to right now save those changes, and that takes a few seconds rather than, so it's resaving all of these meshes, resaving all of these objects that I created, but nothing else. If I was to save the actual whole image, it would take probably 20 minutes or so. So this way it is very, very fast. And this is also a nice place to show this rendering. The ROI tool is pretty neat to show here. So there's a lot of visualization options now. We keep adding them, and I hope you enjoy them as much as we do. We enjoy making them, and we enjoy then playing around with them and getting excellent results out. So that is that. Let me get back to the presentation. Okay. So we did cover all of these demonstrations, and they worked. Everything worked really nicely, so I didn't even have to show any of the videos that I had created before. I want to thank our amazing and inspiring collaborators for their continued support and great discussions. They do inspire us to create the tools that we are developing and then releasing to everybody. And we are currently working very closely with a lot of these researchers. And yeah, thank you very much. The Aivia team has been, as always, outstanding. Even in the midst of a pandemic and with all the distractions that brings, our team, this is the whole team here, has worked tirelessly to create Aivia 9. And I just want to give a few shout out to a few people that have worked on this. So Bryce Kraft, he was the lead developer for Aivia 9, so helped me manage the whole project. And he also worked himself on the new mesh rendering options and helped also with the cell analysis. Casey McBride was really the main driving force behind the cell analysis, multiscale image analysis pipeline and functionality that you saw today. And he also did, in his spare time, the search and action bar. John worked a lot on the measurements for the cell analysis and contributed to a lot of other applications. So thank you, John, also. Hoyen, on the application side, helped create the recipe that you are all going to be using for both the multi-scale image analysis as well as, and I didn't mention that, we have an updated 3D object analysis recipe that creates spots as output instead of meshes. So now you have the option of spots and meshes for the simpler recipe that comes with a 3D object analysis pipeline. Chris, who worked on the instance save and the file readers and many other things that are to come in the future. And Hangyu, who joined us recently and worked already on the Python plugins for CellPose and StarDist, including all the testing and benchmarking. And Chi Xiao, who also worked on those. Patrice and Trevor are really the managers of our GitHub repository, and they keep putting more documentation there, and we're really happy with what they've added so far. We also have a forum that you're welcome to use. That's on our website, where we discuss everything related to Aivia and image processing. All right, so key conclusions. We now have a much more efficient, natural way to do image processing within Aivia. There's major new rendering improvements. The discoverability and usability of the software increases a lot if you have the search action bar on the top, and we have lots of plans for that search and action bar. Naturally, we're thinking about using machine learning to do that and to optimize it and make it smarter, and we're already working on that. We're also made it a lot faster and safer to save, so you can save a lot more frequently. You don't have to wait until the end of the day. And all of this is fully integrated into the pipeline that Aivia offers. So all the way from Aivia to Aivia Web and Aivia Deep Learning Cloud, all of that is connected with the functionality you saw today. So you can leverage everything and build complete pipelines. That's it. Thank you so much. Appreciate that you joined. I know this is a difficult time for everybody. I appreciate especially those of you suffering and having difficulties right now, perhaps not health-wise, but professional or personal. We understand this is a pretty challenging time. It is also for all of us, but we still need to, of course, continue and make the changes that are needed to make our world, our society better. So I think I'll pause there. Maybe there are some questions. I don't know if any popped out.
We do have two from Haley.
Okay, some questions here. Can you import segmented cells or tissue regions for downstream nuclear and vascular detection, perhaps from the pixel classifier? You can, yeah. You can import regions, Kaylee, directly from here. So if you are here, right? If you're doing analysis, you can import regions either here as a ROI. So you can load a mesh, and that's something I just loaded in right now. That's not from this image, so it's totally wrong calibration and doesn't match. But you can load it in there, or you can import meshes from here as well. So import a mesh into here and then process just what's inside of that mesh. So that's definitely possible. Or do you have to apply the whole cell feature within the recipe to determine where you are detecting the nuclei or vesicles? Yeah, so that I think I answered that already. So if you have a label, either you have a brighter region within this channel, or you have a specific label for a group of cells, then you can use them as input in the recipe, right? In the recipe in here, you can use them specifically as input. If you don't, and everything looks the same, then you can import reference regions like I've just done. I loaded this in, and I could run the recipe just inside of that region for the pipeline. Yeah. Let me see what else is in here. Thank you, amazing. Okay, so I really appreciate the comments. This is, as you know, a major team effort. Yeah, a lot of people working on this, and we appreciate all the comments and feedback that you can give us. It's awesome to get it. Okay, let's see if there's any other questions. All right, well, looks like for now that's all the questions we have. I did want to make some basic announcements here, important announcements. You can join our Aivia online workshops. We do them pretty much every week on a different topic. You'll find it on our website. The Aivia Web is now available for annual subscription. So if you want to use Aivia Web going forward, there's an annual subscription. You can use it. It's really nicely priced, much cheaper than buying an actual license. So maybe it's an option for some of you in some of the cases. So contact your local sales and applications specialist. Aivia community is, of course, free to download. So I encourage everybody to go and try it. And there is a promotion for all of those that want to immediately get the new functionality that we talked about today. We have promotions both for brand new users that don't have any Aivia licenses at all. And if you already have an Aivia license and you want to add this module, we also have a promotion for you. Of course, this is time limited. So if you're interested, please do contact your local representative as soon as possible. Thank you. And I wish you all a good, healthy day. Yeah, all the best. Thank you.